Our presenter today is Oleg Ivanov, master student at MSU, who will present his master thesis actually about Universal Conditional Machine. Very intriguing title. Something universal.
Okay, actually, the universal conditional machine is just the conditioning of variational autoencoder, but because the conditional variational autoencoder already exists, we choose another name. The plan of the talk is follows. Firstly, I will briefly remind you something about variational autoencoder. Then I will talk about conditional variational autoencoder, and then about its further extension, our model, which we honestly named Universal Conditional Machine. Then if we have time, I'll talk about some details of this model and of the concurrent model, which is called Universal Marginalizer. So, variational autoencoder is a generative model which tries to learn the distribution over data. The generative process is follows. Firstly, we sample latent representation of the object from standard normal distribution, and then based on it, we sample object using a neural network with parameters theta. So the physical meaning of the process is follows. The point in latent space describes some properties of the generated objects. For example, its class. When we sample a point from prior distribution, we fix these properties and then use a generative network to generate object with given properties. So using such kind of generative process, we can transform a single distribution like standard normal in latent space into some very complex one in the space of objects. So we can see that this generative process induces the following distribution in the space of objects, and we can compute likelihood of them all. But we cannot optimize this likelihood in straight way because we have expectation and the logarithm, and we can't compute it analytically. So we have variation lower bound for model's log likelihood, and we optimize it with respect to the parameters of the proposal network and of the prior network. When we talk about autoencoder models, usually we consider two terms. First term is called reconstruction term or reconstruction loss. It shows how good can we restore our given object. And the second term is just regularizer. So actually, this is variational autoencoder, this picture which everybody draws when talk about it. So I think it requires no extra comments. And here we have the visualizations of latent space of variational autoencoder trained on NIST dataset. On the left picture we can see the generative network representations, and on the right picture we can see the visualization of 10-dimensional hidden space for the different digits. Okay, I think it is clear. One more thing I want to stress that variational autoencoder works with both categorical and real valued data, and that's all. Conditional variational autoencoder. Now we want to learn some conditional distribution. How do we do it? We just take variational autoencoder and condition it on some value. So the result of this conditioning is the appearance of the third neural network with parameters psi, which models the prime distribution over latent variables. And then when we sample latent variable for an object from the prime distribution, we use the generative network to generate the y component of object once again. Physical meaning is similar. On the picture we can see conditional variation of we can see some image from Muniz dataset, and gray pixels describe the y part of object, and other pixels are x part of object. Our prime distribution shows which classes can be corresponded to the observable x. Then we sample, we decide which class we want to generate, and generate the picture.
May I ask a question?
Okay.
Why we have in the previous slide you have explicit link between x and y. Why we do need why we need this link? Don't we assume factorization in this graphical model?
No, actually we can build model without that link, but in the variational lower bound we can condition our y on x. So because this model is more rich than without any dependence, we usually use it.
But it's harder to train because you need, otherwise you can just learn y conditioned on z and that's all. One network for all possible conditioning. And here you need to train a network, a new network for each x.
No, not for each x. We just have an x as an input for our network.
Yes, but we need to take a lot of different x's, a lot of different conditioners here.
Well, actually, when we want to learn the distribution condition on x, we have to have a lot of x. And
So the question, have you tried in your experiments not to use x in the next distribution?
Yes, actually it decreased. The result was the small decrease of log likelihood. The point is that we cannot transmit all information about x through the latent variable. So, for example, if we generate images, we avoid this local information, and we can obtain it only if we have the full access to X object.
Okay.
So, once again, this is log likelihood for variational autoencoder. Now we just condition all distributions on X, and we obtain conditional variational autoencoder. That is really simple. And in the similar way, we can obtain variational lower bound for this model. the derivation also stays the same. What is interesting can we see? We can see that the only way to learn a prior network is the regularization term, because it doesn't participate in reconstruction loss. But when we sample our objects at the test stage, we cannot use the proposal network, so we use only prior network. Some problems. So, once again, that is the principal scheme of conditional variational autoencoder. Also, after proposed in their work to use a model they called Gaussian stochastic neural network. They provide, I think, not very strong motivation about it, but I just repeat it. We will discuss it later in the first section of the talk. So they say we use two completely different networks at the training and at the testing stage, and that is bad. That is bad because actually the proposal network induces a different distribution than the prior network, and for example, we can generate a point from prior network that was never generated at the training stage. So the generative network can be confused by this point, for example. And also they report that the mixture of conditional variational autoencoder and this model gives us better Monte Carlo likelihood estimations. Well, I didn't say what this model is. Actually, this model is simple. We just say that the proposal network and prior network are equivalent completely. When we say it, our variation lower bound turns into the Monte Carlo estimation of lower bound with just one sample.
Can you explain the difference between this formulation and standard training objective?
The main difference is that when we train this function, we sample our latent representations from prior network, not from the proposal.
So P of phi is prior.
P of psi is a prior network, yeah.
So here we're like updating mean, we average over all possible procedures.
Actually, if our proposal distribution approximates posterior, yes, these two models are equivalent. But in practice, this assumption is not followed.
What is y minus b? 1 minus b?
That typo, there is no index for x.
Okay, and why authors use hybrid version if they say that GSSN is better than conditional y? So why do we need hybridization?
They say that the hybrid model is better because it somehow combines the benefits of both models. because it introduces the points from prior distribution into the optimization procedure.
And what is B?
I think no B in this model.
So it is like P of C is just prior.
It should be P of C on Z given X.
So here we are assuming that posterior is always equal to prior.
Yeah, we model them with the same network.
So like posterior does not depend on the actual sample that we have observed.
Sure. If we put it here, we can see that the KL divergence turns into 0, and the reconstruction loss turns into the Monte Carlo estimation of our log likelihood.
So we're just treating two networks, one is normal and one is like broken one.
Yes, we learned the mixture, they share the generative network weights.
But if we train non-conditional variant of the thing, it will go totally crazy because it will just output the mean sample given conditioning.
Yes, that's the point, but that will be later. Okay, why it is called Gaussian stochastic neural network? Because actually, when we do such thing, we turn our model into a single neural network with one Gaussian stochastic layer in the middle. Now it can be trained completely without any breaks in the middle. Okay, and here we can see some the example of how this model works. X is the upper part of the image, and we can see that the lower part of the images are generated rather diverse and rather realistic.
Rather diverse, there are no 3, for instance.
Here it is.
Only one. Looks like mode collapse mostly.
On the first picture there is 3. 3 mixed with 2.
Actually, we're like forcing explicitly our model to collapse into single mode in this formulation.
No, when we use conditional variational autoencoder, it does not collapse.
But given conditioning, if we force alpha to 1,
Yeah.
we will force our model not to look at Z at all, and just output the same image for given X.
You mean to 0, but here we use alpha close to, well, we use only a little part of Gaussian neural network in the mixture. Okay, so conditional variation autoencoder is a model which can be obtained very simple from variational autoencoder. It is very useful when our conditional distribution is complex. For example, it has several models. Actually, it has 3 neural networks to learn instead of variational autoencoder, which have only 2 of them. And authors propose the modification called Gaussian stochastic neural network. So now we go to our modification, Universal Conditional Machine. We want to learn not only one conditional distribution. we want to learn the distribution over the vector and to be able to condition it on all subsets of its components, of its features. So at the testing stage, we have different objects, and for each object we want to restore the distribution over the missing components somehow. To write the model down, we introduce missing features mask. It is just a binary vector corresponding to each object. 1 in this mask means that the component has to be restored, and 0 means that we observe this component. And we use the following indexation notation. X index B means that the subset of non-zero of missed components of the vector, and X index B means all observed components of the vector. So, what problem we want to solve? We want to obtain a single model with some parameters which can restore the distribution over xb given x1 minus b. And we want actually we want to restore joint, complex, multimodal, and so on and so forth distributions. So why do we want to restore distributions? Because if we do some point estimation for the objects, we lose information. So the distributions are much better. Our generative model is very similar to the generative model of conditional variational autoencoder. Here we have the observed components of the object and a binary mask of this object. Based on them, we generate latent representation using prior network. And then, using this latent representation and the observed part of the object, we generate the missed part of the object.
But the size of x, of known part of x, is different for different x's.
Correct. When we work with neural network, we just use element-wise product with a binary mask. So we
so you put all x
yeah.
with just zeros for non-known values,
Yeah.
and this mask.
Okay, once again, the physical meaning of the process is exactly the same as for conditional variational autoencoder, but we have a little bit different likelihood of the model. We can compute the probability the probability density function on the missed components given observed ones. But we know that the model cannot work ideally. So for some masks it will work better, for some it will work worse. And in order to say model about which masks we care most and about which masks we care least, we introduce the distribution over masks, and we can assume that we generate some samples from real distribution, generate some samples of missing feature mask distribution, and we compute the log likelihood of our model over these two distributions.
Is it true that we compute log likelihood only on values that were not under match?
Yes, we compute log likelihood only for missed features.
Is I'm right that in the conditional autoencoder you can like condition on any y. It may be a class or it may be any other variable, and in this method we can condition only on missing part of x.
Well, actually, in conditional variation autoencoder, we have conditional distribution over y given x, and here we can condition on for every object. We can condition on every subset of its features.
In the conditional autoencoder?
No, in the universal conditional machine, we call it universal conditional machine because it can be conditioned on every missing feature mask we.
But is it possible to condition on class?
Yes, we just concatenate the feature representation of object with its class and learn model on such object.
Yes, but it's not written in notation.
Well, it is, I don't know, preprocessing.
I have a really weird question. Imagine that P of x given z is autoregressive distribution defined by recurrent network or something like pixel CNN or pixel RNN. Then to obtain distribution over next symbol or pixel, we should pass previous pixels to it.
Yeah.
And which pixels should we pass to it? A real one or like predicted?
Well, if we compute log likelihood, we have to pass the real one. Sure. Well, it is just a chain rule. If we have the probability over x.
Oh, yes.
It is usually called teacher forcing when we use the training sample here.
And we partly teacher force and partly sample here. When we want to obtain sample from our model.
The only generative because we have no access to.
So when you have true variable, we force it. Like and when we don't know the true answer, we sample it from our model.
Well, on strain phase we force it, and on the test stage we sample it. That's how it works.
Only those that we don't know true answer.
Yes, if we observe the feature, we have no need to sample it. So, okay.
By the way, what the distributional masks do you use?
Different distributions for different domains. For usual sets, we use just uniprobable distribution of the masks. For images,
Uniform distribution?
Yeah.
Okay.
And for images, we can use Bernoulli masks, but then we have to solve interpolation problem, it is too easy. Even if we lose, I don't know, 90% of the data, we can easily restore the image. So we use structured masks like rectangles or something like that. So once again, we have variation lower bound, which is derived in the similar way. We have the similar network structure, but here we have different inputs to the proposal network and to prior network also. And okay, we can use the networks of every complexity inside our model. For example, when we work on the SLAM dataset, we used ResNet based autoencoder solutions with steep connections between prior network and generative network. And these steep connections between prior network and generative network are exactly what you were asking for. It is the conditioning on the observable part of the image. So by this steep connection, our model looks at x dot 1 minus b. Okay. So once again, we can use Gaussian stochastic neural net, but we highly not recommend to. And we made several modifications of this model. For example, the first problem statement assumes that we have the access to full true data distribution, but the common case is when both train set and test set contain some missed features, for example. And for that case, we can just marginalize our prediction of missed features, and it results that we just do not count them in our log likelihood. And also to do that, we surely have to condition our mask on our object, because we cannot give something like none into the input of our network. So, like everybody, we used the variation of the coefficient before KL divergence during a training procedure. We found it essential when we learned on discrete data sets, but for image and painting, for example, it is not that necessary. And when the coefficient between KL divergence is small, we learn good Laplace representation and proposal network, and after that we linearly increase it and learn our original model and prior network.
Why do you say that latent representations learned with zero divergence are good, better than with coefficient 1?
Well, okay, the point is that when the coefficient, the coefficient before KL divergence is 0, we have no extra restrictions on our proposal network, so we can learn just to autoencode the observed part of objects. And if we set the KL divergence coefficient to 1 At the start of the training procedure, it just
Actually, convergence forces forces latent representations to be smooth, and without it, autoencoders learn very sparse. I mean, by sparsity, I mean representations of different objects are very far from each other.
well, actually, here it doesn't work because our prior distribution is also modeled by neural network, so we have no restrictions about the shape of distribution in latent space. Potentially, our Z can.
But it is still Gaussian.
Yes, it is still Gaussian, but potentially that can tend to infinity, for example. Well, we never observed it, but
Oleg,
yeah.
am I right that you have shaded for coefficient?
Yeah, sure.
So, okay.
Yeah. Okay.
What representations do you consider good?
Well, good representations is the representations which help us to solve the problem. I don't know how to answer.
It's clear from pictures.
Okay. Well, actually, when we start with one, we have no diversity in our learned distribution, and that's bad. And that is why we first learn autoencoder and generative network to make diverse samples, and then we feed prior network to sample from the generative network properly.
So actually, when you are training without chaotic versions, you're just training denoising autoencoder.
You can say that, I think. Yeah.
Except denoising usually happens at the observations level, not somewhere deep in the network.
But when we're training Gaussian stochastic neural network, it looks like just vanilla denoising autoencoder, because we're not conditioned on real sample.
Yeah. But neither is input anyhow. Neither is input similar to the output. It's just some random noise.
In which case? In case
In
of
the case of
standard,
the-
why we
The second one, the Gaussian
Yes.
stochastic networks.
Okay, let us skip this part and go to some experiments we have. The first experiment is about using our model for missing feature imputation problem, actually for multiple imputation. Because if we learn distribution, we have to have some benefits from it, and the benefit we have is that we can restore the missed features in different ways. So what we do, we take some popular data sets, we randomly throw out half of the features, and we use our model to restore the missed values, and we can compare it with the average imputation. We compare it with the standard method from XGBoost library to handle missing features, and with multivariate Gaussian, which is also can be used to make multiple imputations.
do you find a maximum maximum likelihood solution, or you just sample?
Just sample. That's the point.
But all these data sets are very small. How do you learn 3 networks on this?
Well, networks could also be small.
Like 5 parameters.
No. Actually, because we learn arbitrary conditioning, we have
Exponentially large data.
yes, that's the first point, and we have to use a normal size of networks to learn such dependencies.
So you augment the data for all possible missing parts?
Well, when we learn our model, we sample missing feature masks from our distribution, which is actually uniform.
So we can sample many masks for,
Yeah.
for the same object.
Yeah.
And anyway, which architecture do you use for the networks here?
Uh,
Like for wine, for instance. Wine is like 100 objects, so
No, wine is larger, for sure.
Did you compare it to vanilla denoising autoencoder?
One moment. The architecture was multi-layer perceptron with about 3 or 4 layers, about several hundred units each. And denoising autoencoder, actually no, I didn't.
Actually, I think it would be really interesting to compare because like the difference in model is that denoising autoencoder assumes that missing features are independent of each other given other, and YA doesn't have this assumption. So on structured data, this should perform better, like on text, for example.
Well, actually, denoising autoencoder, I think, lies a little bit aside because it doesn't restore the distribution.
You can you can view denoising autoencoder as a conditional model also, and you can train denoising autoencoder with Bernoulli masks, and in this formulation it will be actually equivalent to your model like with Gaussian stochastic neural network approach. KL divergence is 0.
Well, I think it will lack of the data multimodality because we need some.
Yeah, yes, but actually you can somehow solve multimodality and independence problem by first of all you can solve multimodality problem using some kind of Gaussian mixture in outputs and stuff like that, and also you can use Gibbs sampling to Gibbs sampling like procedure to sample from joint distribution using a denoising autoencoder.
Well, okay, I'll think about it. Thank you. But now the second experiment we have, it is image generating. It is much better because here we have pictures and we can observe them and say what we see. So the left column we see is the input to our model. The gray pixels means missed part of the image. The right column is ground truth, and the middle is samples from our model. You can see that samples are different, diverge, and kind of realistic. So actually the model solves the problem. And it solves the problem not only on MNIST dataset, it solves the problem on Omniglot dataset also, and on Celeb dataset, and that's all for now. As for datasets. Well, okay, the outputs are blurry. It is the common problem for variational approach, but the rest works fine, I think.
It's okay.
Okay. So our model can learn arbitrary conditioning. It can be considered as the further extension of both conditional variational autoencoder and just variational autoencoder. We can incorporate some knowledge about the problem specific by choosing the mask distribution, and we have modifications for different cases. Okay. Yes. So now I have two stories left. First story is about hybrid model. Actually, it is it's not connected only with our model. It is connected with conditional variational autoencoder and just variational autoencoder because actually it is very similar models. So once again we have a mixture of two models and some motivation actors provide to explain why it is good. Now we just look at this and verify it. So they say that hybrid model have better Monte Carlo log likelihood estimations. The reminder what is Monte Carlo log likelihood estimation and what is importance sampling log likelihood estimation. We have our model which have the expectation under the logarithm, and we can approach to this expectation using samples from prior network, or we can use more complicated technique. We use samples from the proposal network, which tells us the region we must use to sample object which looks like the missed part we have to restore. And we have the following formula for the sampling. Is it familiar to the audience? Okay. So on our data sets for image in-painting task, we actually observe that, for example, for Omniglot, the Monte Carlo estimation for Gaussian stochastic neural network is better than for our model. But when we use importance sampling log likelihood estimation, it is much better. So it is not a good reason to use Gaussian stochastic neural network. It just means that Monte Carlo estimation is not precise enough for variational autoencoders and for our model. The second argument they use is that the latent space in variational is that our proposed samples are different from prior samples, and that cause some problems. Well, we have to agree. That reason we can provide very simple example why it is bad. Suppose we solve so-called XOR problem. We have the distribution over two-dimensional binary vector, which looks like chessboard. You can see it on the image. If we have two Gaussian normal proposed distributions, we can see that there is an area where these two distributions overlaps, and in that area, generator have to generate the Bernoulli parameters of 1/2 for both components. And also there are some areas of low density for both proposal distributions, but with rather high density of prior distribution, from which we don't know what generator will generate. So even on this very simple problem, vanilla variational autoencoder will not learn this distribution precise enough. It will learn some smooth version of it, and it is the fundamental problem of variational autoencoder. But it can be solved using normalizing flows or something like that in this area.
Normalizing flows is a prior or in the posterior expansion.
Well, actually, here we can see that we have both kind of problems with the posterior distribution and with the prior. Posterior overlaps, and prior have some spaces which are not covered by posterior distributions. So, and what we do when we learn Gaussian stochastic neural network, actually it really leads to unimodal distribution. Why is that? Suppose we have pre-trained model with two areas in latent space. The red area corresponds to the one point, and the blue area corresponds to another point. When we sample from the proposal distribution, it is okay, but when we go to the Monte Carlo estimation with one sample, we have our Latin representation equiprobably in the blue area and in the red area. Using Monte Carlo, when we maximize the Monte Carlo estimation of log likelihood, we will learn the unimodal distribution, even if our model was pre-trained to be multimodal. And to finally decide whether use Gaussian stochastic neural network or not, we test it on the syntactic data. The distributions is on the left. We see that when we use the mixture coefficient 1, which means that we do not use Gaussian stochastic neural network at all, we can restore our distribution more or less good. But when we turn alpha to 0.99, the distributions, the restored distribution is more smoother. And when alpha is 0.9, the whole distribution structure is lost. So that is the reason why we do not recommend to use alpha not equal to 1. So there is some takeaways. The main idea: do not use Gaussian stochastic neural network. And the last part of the story is universal marginalizer. Actually, in the paper, it was applied only to sampling from binary graphical models, so we have to improve it a little to make it work. But after we improve it, it works good. So, what's the model? Like in our model, we have binary mask of missing features, but we want to learn a model which restores not the whole distribution over the missed components. It restores just marginal distributions for each component. So it has completely, not completely, but rather different work likelihood.
So it's pseudo likelihood.
Why pseudo? No, it is fair likelihood.
Because you do not model any correlation between components of observed variables.
No, we don't, but the goal of model is to learn marginals. So
Our joint distribution is not a product of marginals.
yes, but
But we have latent variables.
we don't want to learn joint distribution. For now, we want just a model to which we give the observed variables, and it produces the marginal on each components. Because it produces marginals, they are not supposed to be correlated somehow.
So the mask here is what variables we're trying to marginalize over.
Yeah. Well, the mask is the set of components for which we want to obtain marginal distribution.
Well, the variables for which mask is not one are not assumed to be independent here.
Yes, we just condition on them. Well, okay, if we have, I don't know, an image, we have the observed part of the image. We don't want to restore this part of image. We want to, for each pixel, we want to say that it is 0 with probability 0.8 and 1 with probability 0.2.
But for each pixel or for each configuration of non-masked pixels?
For each pixel, independently. So that is the model. We can see it uses only one neural network.
Sorry, stupid question, but why, if we consider all pixels independent, why do we need a mask?
We consider we want to compute the marginal probability for this pixel given the whole unmasked part of the image.
But here you say nothing about other pixels that are not unmasked, that are not under mask. So
About these pixels?
yes.
We just don't care. We want to restore the distribution over this pixel, the marginal distribution. It does not depend on the marginal, it's marginal distributions of the other pixels.
This is a strange assumption.
Well, that's not assumption. That's.
Oh, I understood. Yes, okay. That's right.
Okay, any more questions? Okay, so we just have one neural network model, and we now we can sample from joint distribution using this model and chain rule. What do? We have conditional marginal distribution over some pixel. We sample it, we add it to the observed pixels, and repeat this procedure until we sample the whole image or the whole object. Okay, let's consider we have x in 5-dimensional space. We observe x3 and x4, and we have to restore the distribution over x1, x2, x5. We can write out that the probability of x1, x2, x5 condition on x3, x4 equal to the product of the marginal of on x1 given other components dot marginal over x2 given x3, x4, x5 dot the probability of x5 given x3, x4. That is the chain rule, and we can use it to sample our object from joint distribution.
Well, this is the correct model, but you used instead in previous slides, and not this one, but you use a product of one-dimensional marginals of xi conditioned only on x3 and x4.
Yes, but we have different binary masks, so when our masks goes through all possible values, we learn all these distributions. What we learn is and our objective is the product of all such values for E mask, and we have some expectation over all masks. So if we perfectly learn this model, then this is correct.
Actually, there is a white-out paper called Masked Autoencoders for Distribution Estimation. And they're doing very similar thing. They have fit for neural network, and weights of this network are masked in such a way that with respect to some ordering of variables, network is autoregressive. And at each iteration, they sample a random mask that respects the property of progressiveness, and train this network to maximize likelihood, like we do for all autoregressive networks. And it's really similar to the approach you're using.
Well,
with the difference that they use masks for weights and you use masks for variables.
well, I think that is significant difference. But anyway, that is what they say in the original paper. And after that, what we say? We say that actually we can sample our object in different orders, not only left to right. We can sample our object by sampling random components, or we can do we can sample it in any other order. What we want to say is that this model is completely not working because when we sample at the testing stage, our model uses a completely different distribution over the masks than at the training stage. well, if we consider the distribution of the masks as follows, that each mask is a rectangle, but then on the test stage, our masks would be like a rectangle, and some upper part of the image are visible, and the rest is not visible, for example. So we have to introduce some distribution which is well, we have user-defined distribution over masks. We have to modify it somehow to make it consistent at the train stage and the test stage. And actually, we can do it for both left to right sampling, but we don't like left to right sampling because it is very, it might be very biased. And for sampling components in the random order, we have just to multiply our mask on the Bernoulli masks with a uniform probability of a component to be 1. So well, actually, after we do it, the model started to work, and it produced good samples, and the model takes into account the local dependencies between pixels, which is not done so straightforward in variational autoencoders, for example. And so what we can say about the model, first we have to modify the distribution over masks to train the model consistently. But it takes about 1,000 times more time to get one sample on NIST, for example, than from our model, because we have to use a neural network for sampling each component sequentially. And but the model works maybe better. And the intuition behind it, actually we can consider this model as the extension of the pixel CNN. So the relation between our model and this model is somehow similar to the relation between variational autoencoder and pixel CNN.
Is that all?
Yes, that's all I can say about it.
Okay, I have a question about conditional generative adversarial networks. Are there any, and is it possible to combine them with conditional variational autoencoder?
Oh, okay, that is a good question. Actually, there was 3 reasons why we decided to arbitrarily condition variational autoencoder, not generative adversarial networks. The first reason is that we want to be Bayesian and so on. The second idea is that generative adversarial networks don't work so good with categorical features. And the third idea is
but
that
here you don't use categorical features in all your experiments.
On MNIST, features are categorical.
NIST and some data sets. And the third reason is that generative adversarial networks tends to mode collapse, and when we want to restore the distribution, we don't want to have mode collapse. But yes, actually there is a paper called Conditional Generative Adversarial Networks. They conditional generative adversarial networks in the similar way. They just conditional distributions, and it works. And we can do universal conditional machine generative adversarial, but we still don't. We want to have sharper image samples. So we are working out.
You can use like perceptual loss.
Some, yes, some connection between variational autoencoder and generative adversarial network to do so.
But when you add some adversarial loss or perceptual loss, the problem is you don't have proper likelihood, and you have to somehow tune the weights of the tail divergence, and it is really tough work to do properly.
Yes, we want not just to make a random mixture of models, but we want to have some probabilistic interpretation.
Like AlphaGun.
Well, better, because AlphaGun, well, we have problems in the interpretation. Okay.
Any more questions?
Yes, how does the model generalize to other types of masks that it was not trained to train for? Like, if you train with square masks, will it work for just random independent noise?
Well, surely it works better when we use completely different distributions on the masks on the test stage and on the train stage. Well, it is not the silver bullet, so I think it is quite intuitive behavior.
Okay, let's thank the speaker for interesting talk.